All right, welcome everyone to this Tuesday afternoon. This is another talk in our series of digital science, scientific computing talks that we are arranging. As a bit of background, as you know, this agency is recognizing that the world is changing rapidly, the technological world, and because that's changing, we must also change the way we do our science and really embrace these new digital science principles and technologies. Some of the things that are changing is that, frankly, the complexity of the questions we are expected to answer in the future are far different to what they were just 5 years ago. We are asked to understand the interaction between surface water and groundwater. We are asked to provide a geodetic datum that will bring GPS accuracy down to 1 centimeter. We are asked to look for minerals and resources kilometers under our sediment, and we are asked to use in remote sensing, for example, to create new novel objects like lakes. What is the probability of this lake being wet? When was this river mouth open and closed, for example? Also, the amount of compute around is unprecedented. I mean, we can do things on our smart devices that we couldn't do on a desktop only 10, 15 years ago. Also, the expectation from the world is that things are available automatically and online. So we are really realizing we must change the way we work. And one of the things that we have identified is that there is a lot of new scientific computing techniques that are really cross-cutting across the agency, whether that be fluid mechanics, fluid flow modeling, or real-time processing, or statistics, or machine learning is one of the things that are coming up as a new way of starting to predict what we cannot observe. So this talk is about machine learning, an introduction to machine learning and what can be done with it. And it's given by Gabriela Ferraro, who is I'm just going to consult the notes here. She's a researcher in machine learning at Data61 CSIRO. And she's also an adjunct professor at engineering and computer science at the ANU. Gabriela got a Bachelor of Computer Science in 2004 at the Champagnat University in Argentina. In 2005, she received a master's degree in Science of Language and Applied Linguistics at the Institute of Applied Linguistics in Barcelona. In 2006, she joined the Center for Autonomous Systems and Neurorobotics at the Department of Information and Communication Technologies at Universitat Pompeu Fabra in Barcelona. That's Catalonia, I understand. And she received then a PhD in Information, Communication and Audio Visuals at that same university in 2012. And then I believe she came over to work for NICTA and CSIRO, right? So her interests are machine learning for natural language processing. And although it's natural language we're talking about, I think you will all be able to see a lot of parallels to geoscience from what she'll be talking about. And her other interest is in deep learning for information extraction applications. So without further ado, please welcome Gabriela.
Thank you. So, hello to everyone. So, thanks for the introduction. So yeah, this talk is an introduction to machine learning. It's not a tutorial or a course about machine learning. There are plenty of amazing courses about machine learning online, and they are free. And I will give you the links at the end of the talk. Okay? So, briefly, the outline during the talk will be at the beginning try to describe what is the language that we use in machine learning, so you can get familiarized a little bit with the terminology. Then I want to talk about what are the types of machine learning problems and what are the machine learning techniques, so we don't want to get confused between problems and techniques. And then I will give an example of machine learning workflow and what is the pipeline and what's the methodology we follow. And the second part at the end of the talk will be to give some practical advice for debugging machine learning algorithms. And I will go also to give you some resources to study or to go more through machine learning, okay? Okay, so what is machine learning? So there are many definitions, okay, and I just put here 2 definitions of machine learning. Say, for example, it's a type of artificial intelligence that provides computer with the ability to learn without being explicitly programmed, okay? And that sounds very fancy. Let's go to the second one. Machine learning is a subfield of computer science that evolved from the study of pattern recognition and computational learning theory in artificial intelligence, okay? So these are kind of an overview of the field. So what is machine learning? Machine learning is all about prediction, okay? So in machine learning we have examples, we have data, and this data have to be a lot. We have labels of annotations of that data, so we have some answers about that data, and what we want to do is to learn a predictor, okay? So this predictor is a function that will map, let's see if I can use the mouse, will map our examples, okay, our futures and our examples to some labels. So what we want to do is to learn this mapping function, okay? And that's what we call the predictor. So given some data, given some examples and some labels, I will want to find this best predictor. And that's what we call supervised learning, okay? So to do supervised learning, we have to have a lot of data, okay? And these labels, so the outcome, the answers that we want to find, they are usually binary, okay? But there are also another type of machine learning that is what we call unsupervised learning, okay? And in this kind of learning, what we do is to detect patterns in the data. I will give examples of supervised and unsupervised learning, but the talk will be more focused in supervised learning because it's more interesting. There are more things that we can do with that, okay? And there is a key point to understand machine learning. Machine learning is about prediction, but prediction doesn't mean understanding, okay? And that leads to the second slide that say that prediction or correlation does not imply causation, okay? So if we want to do science and have questions about science, we should ask about causation, because prediction sometimes won't give us the answers, okay? The causes of the problem. Okay, so let's talk about what is the difference between the machine learning problems and the machine learning techniques, okay? So as you might know, a problem is defined by the data you have and what you want to do with that data, okay? So we said that machine learning is about prediction. We want to find a predictor that fits our data, okay? And examples of machine learning problems are, for example, classification problems, clustering problems, the dimensionality reduction in problems, and so on. But when we talk about the technique, okay, so a technique is the method for finding a solution that is applicable to the class of problem we want to solve, okay? So we want to search through the space of possible predictors and evaluate, okay? So we want to find the best predictor. Usually we will try different predictors and try to find the best to fit our data. And examples of machine learning techniques are, for example, supervector machines is a kind of algorithm. K-means is a kind of cluster algorithm that you might know. And for example, principal component analysis is also another kind of technique. Okay? So let's see more examples of supervised machine learning. So depending on the problem we have, is the type of algorithm also we want to apply. Okay, so for example, if we have a problem that is a binary classification problem and we have a pollutant and we want to see if this pollutant is important for quantifying the air quality or not. So it's a binary classification, is this important or is not important? But we also can have multi-class classification problems, for example, gender text classification. So if you have a lot of text and you want to classify them in different genders, like geography and history and so on, you will have different labels, no? You will have a multi-class classification problem. Other problems are, for example, regression. So in this case, the result, it won't be a label, it will be a number. So you want to have a ranking. For example, examples of regression problems are, for example, recommendation systems. The web results from Google also is applying a regression algorithm. Sequence annotation as the problem, for example, of machine translation and speech recognition, where you have a sequence and you want to decode that sequence in something else. Another problem, for example, is hierarchical categorization, for example, ontology population or image recognition. And I will give some examples of these type of problems. And what we have, as I said before, we have this function that is our predictor. We have the labels, that's the answers that we want to learn. And we usually have a last function that we want to minimize, okay? We talk about that later. So this is an example of supervised learning, and this is a filtered binary classification solution. So you can see here there are two groups. One group is a spam email, the other one is not spam email, okay? Very intuitive visualization. Another example of supervised learning, multi-class classification. In this problem, we have an image, okay, that can be one of these small individual images at the top, and we want to find a digit of these images. So this is the problem of character recognition. And in this case, yeah, it's multi-class because we have many numbers, okay, and we have to find what is the number given a picture. So let's see some examples of unsupervised learning. So this is the learning where we don't have the answers, we don't have the labels, so we just want to estimate something. So given some data, we have to ask a question about that data or about the model that we want to build for this data. Clustering is usually one of the most known supervised learning techniques, and it's a really good technique to explore your data. Okay. Also, principal component analysis, sequence segmentation, for example, using hidden Markov models, and so on, and cases of unsupervised learning. Why could I find the odd one out? So clustering is really, really good to find outliers, to find things that are unusual in your data. Okay. So this is an example also of unsupervised learning. So we can cluster or group, for example, documents, users, web pages, diseases, and so on. The difference between classification and clustering, that is grouping. In clustering, we don't have labels. We have groups, but we don't know what those groups mean. In classification, we have groups, and we know the labels of those groups. So this is an example of hierarchical grouping done with some clustering, and in this case, as you can see, they are organized in pictures by colors and also by flowers or by the picture themselves. So this is the kind of representations we can have as a result. And when we talk about machine learning, there is no need that you code all the machine learning algorithms because there are plenty of algorithms out there and different libraries you can use. I'll show you more libraries later, but you can have an overview here of this Python library where you can find some classification algorithms or regression algorithms and some ideas of what is the problem you have, what is the algorithm you should be using, okay? Okay, so let's go now to more deep into supervised learning, okay? So in supervised learning, we usually have this pipeline, processing pipeline, that is mainly composed by three main steps. The first step is the data gathering. So we have to get some data, okay? So usually the data gathering can be split in three steps. First, we have to collect some data. We have to label that data with the answers we want to predict later. And we want to partition this data into different sets. And we'll talk about later how to partition that data. It's very important. After we have the data collected, we have to do some feature extraction. What does it mean? We want to extract features from our data that characterize that data. These features, we'll see an example later, I usually represent this as a vector of numbers, but they also can have other different kinds of values. So with these first two bubbles is what we call the second step of training. So our data and in our futures, we were able to do the learning of the algorithm. For learning, we have to also tune the parameters of our algorithm, okay? And by tuning and training our algorithm, we finally will find the best model, okay? And with that model is with the one that we are going to do our predictions. So this is kind of the classical pipeline. So when we talk about training and developing, they are apart from the feature extraction, the parameter learning and the model selection, these steps are done in a loop. Now we have to do this all over again till we find the best model. How we can do that? Because we can perform some evaluation, okay, and we can test the performance of the predictor because we have the labels, but we also can test the performance of the predictor with unseen labels. And we see that in a minute. And it's a key to understand what is the difference between training and predicting, okay? So in this picture, what I try to show is some data. In this case, is some genomic information about some genomic sequences. These data have some labels, okay? So this is categorized as true, and this is categorized as false, whatever that means. So we have, after we have the data with our labels, we extract the features. We put these features in some numerical space, and we do the training. And I don't know if you can see from there, but here we have some nodes that we have to adjust, and those are the parameters of our algorithm. There are many ways of tuning those parameters. You can do it deterministically, or you can do it with a search. That is going to be more costly, but most efficient. So after the adjusting the parameters and training, we have as a result a model. This alpha model, okay, is the model that we will use later for predicting. So when we are in predicting time, we have another data, okay, that is not the data that we use for training. We have some numerical representation when we extract the features from our data, and we use this model, okay, to predict labels. So that's the key. Training is about using the data to learn your model. Predicting is about using the model you learn with the data, from the data. Okay, so we said that we can measure something because we want to find this best model somehow, no? So how we do it? What is the things that we want to measure? So basically what we do is to estimate the performance of the predictor by trying to see what is this generalization error. We want our model to be general enough to be able to predict things on unseen data, okay? But we don't our model to be too general, that is not going to have good predictions at all. And how we do this? Okay, we can estimate the expected risk with the empirical risk because we have some data that is labeled, and we use that data to have an approximation of the performance. But there are also other techniques like cross-validation and bootstrapping that you might be familiarized or not. I'll talk about a little bit later. Okay? So let's see what we measure. Okay? So we usually measure something that we call accuracy, and this accuracy can be macro, micro accuracy depending on what you want to test. So we often care about the overall accuracy of our classifiers, and we treat and we call this the macro average, and this is very easy to compute. It's the number of correct classification divided by the number of the total samples you have in your evaluation data. And also sometimes we want to compute the macro average because in this case we want to treat each class equally. Okay, so imagine that you have many classes, and for class number 1 you have just a little examples, and for class number 2 you have thousands of examples. Because machine learning works with a lot of data, the prediction of the class number 2 will be much higher. But sometimes we don't care about that. We just want to treat every class as the same. So in this case, we compute what we call macro average. And sometimes we also want to compute the weighted accuracy. And I'll show you how we can get these numbers now, okay? So in order to compute accuracy, we have to treat our data, our errors in a special way, maybe in a way. So what we have here is called a confusion matrix. I don't know if you are familiarized with this matrix. And we have different types of errors that we want to know about our data. So we have what we call true positive. True positive, it means that you hit the detection, it means that your algorithm is doing fine. When you have true negative examples, through negative examples is a correct rejection, so it still is a positive outcome and it's not an error. And then we have two different types of error, what we call false positives and false negative errors. And we see this with an example later. So when we can compute for each of our examples which error type they are, we can fill our confusion matrix, and we can compute recall, precision, accuracy, and the specificity of our model. And we can also compute the F-score, is just the trace between precision and recall. We see this in a few graphs later. Okay? Sometimes we don't have a big test set, so we don't have a big set to evaluate our data, and what we do is to use a method that is called cross-validation. In this method, what we do is we have all the data, we partition the data in different folds. In this example, we partition the data in 10 different folds, and we use all the data but one partition for training, and we use then that partition for testing. In this way, you are using all the data for training and all the data for testing, but not at the same time. It's okay to do this when you are in the development and in the training of your algorithm, but it's not a good idea to do cross-validation when you really want to test the predictor performance. Okay, so now I want to show you quickly an example of the pipeline with a classification problem of name entities in text, okay? And I'll show you what is this. So in this problem, what we want to solve, what we want to do is we have a piece of text, that is this piece of text, and we want to tag this text with different entity types. For example, we want to identify if they are persons and which are them, if they are organization names, if they are location names, and so on. Okay, so this is the problem. I have a text that have no labels, and I want to put these labels or these highlighters on the text. So in this problem, we can see that every word is a possible entity. So every word in this text is an example of the data I will use for training, okay? And my computer, or the computer, has to learn what an entity looks like, okay? So that's the future engineering, what we call giving some examples of those entities. We want to see how they look like, okay? And then we want to predict on, after we build the classifier, on unseen examples. So the classification of name entities is a type of supervised learning. It's a class of sequence labeling problem because text is written in a sequence, okay? And for this example, what we did is to apply an algorithm called condition random fields, and I'm not going to go into the details of that, just show you the example. So first of all, I have my data, okay? And I want to split this data into three different sets. A set that I'm going to use for the training, a set that I'm going to use for the validation of the development of the model, and a set that I'm going to use for testing, okay? So when I'm doing the training, I'm going to learn the model parameters. When I'm using the validation set, I'm going to tune the meta parameters of the algorithms. And then when I'm doing the evaluation test, using the test set, I'm just going to report the performance, okay? So let's see an example of how the training of this algorithm that recognize entities looks like. So here what we have is the data, the text is being put in a column, so words is in a line, and this is the data, okay? And these are the labels. So for example, US, the label is location, Mark, the labels is person, and so on. This problem is easy because you don't require an expert to realize that Mark is a person name. But some problems, and many machine learning problems, require the expertise on the field. For example, if you are classifying genome sequences, you need a biologist. It's not enough to have a computer scientist, and so on, no? So this is how the data will look like. We have the data and we have those labels. And I want to go from the text I have to the features, because I want my data to be characterized by a set of features that I will use for my classifier, okay? So I said before, sometimes examples I represent this as a vector of features. These features are usually numeric values, okay? And you need the expertise to design good features. So for example, what would be a good feature from person? Well, I can say, for example, that a string like this, like a capitalized with a dot, is a good indication. I will say like a capitalized word is also a good indication of a name, of a person name. If it is, if the words are all capitalized, it might be an indication of an organization, okay? I also can use some kind of diary or gazetteers that say, yeah, indeed, this token or this word belongs to a dictionary of persons, so it might be an indication of a person. So this is the way I extract the features, okay, for this example. So let's see how our data looks like once we add the features, okay? So at the beginning we have the data and we have the labels, and in the middle of this table are added a few features. So for example, I've added 2 features, the grammatical category of each of the tokens, and also in a binary notation if the words are capitalized or not, okay? And this is just an example. We usually put more complicated features. We also put, so for each word, we will have a vector of features. And to do feature selection, there are many methods, but I'm not going to go into the details, but this is very important. When you do feature engineering, you have to go through these methods. You have to, for example, filter your features, or you have to incrementally add features to test what are the best features for your algorithm. There are dependency between features, there are correlations between features. Sometimes you take one off, the performance will go down. You don't understand why. So it's important to do a little bit of work when you are dealing with the feature extraction. So after we have the features, we can go for the training, okay? When we go to the training, what we do is to learn the model parameters. And for this step, it's very important that you use the training set, the first partition that we saw in a previous slide. After the training, it's time to do the model selection, okay? So you will fine-tune to get these best parameters for your model, and for this, you use the validation set, okay? It's the second set we saw. And when I said that we are going to tune the parameter, what does it mean, okay? So it means something like this. So let's say that you have a model, that you have a very simple model that is able to recognize only person names, let's say that, okay? And I want to change stuff of this algorithm that I'm using. For example, I want to change the label weights, because I think some of the labels are more important than others. I want to change the regularization parameter, how much is risking to get minimizing that loss function we said before. Sometimes I want to run the algorithm for more iterations. So all these things, I try different configurations, and then as a result you have different models, and then you have to choose the best model. Also, when we're talking about how to tune the features, sometimes you want to do similar stuff, no? So after training, finally, after training and selecting our best model, we can use this best model to see what happened with unseen examples. And for this, we use the test set. So let's go again with this example. So we have the features, we have the data, the features, we have those labels, and I have my algorithms that is predicting in this data. And the algorithm is doing sometimes correct, but sometimes he's not doing correctly, okay? So that's why there is always going to be a difference between the labels, the gold standard, and the prediction. Prediction is always to be much lower or less or lower than what we can do with the labels themselves. And so when I'm going to do the evaluation of this predictor, I can compute, as I mentioned before, this kind of numbers. So if I have location is a true positive, it's a hit, did it correct. this guy is incorrect, so it's a false positive. He thought it was positive, but it's false. Person is true. It's a false negative, and then we have some true negative. So when we have this, that is very easy to compute because you have the labels and you have the predictors, you can compute metrics like precision, recall, and accuracy and see how well your model is doing, okay? We said that a machine learning algorithm is learning something when this number, this accuracy, the overall performance is above 70 or 7, and the maximum is 1, okay? So if your algorithm is below that number, it seems that things are not doing very well. So how we know this? How we know how good can we go or how bad can we do with our performance? So there is usually what we call a lower bound and an upper bound. Okay, so a lower bound would be a baseline. For example, random assignments of the labels. That will be a very low baseline depending on the problem. Sometimes random assignments do quite nice. And then we can also have an upper bound of the performance, okay? So for example, can the computers do better than humans? I don't know. So some Google claimed last year, I think it was, that for image recognition they were doing better than humans with their machine learning approach. So they asked humans to classify images in different categories, and they give the same set to different people, and after the classification, they calculate the agreement between the annotators, and the agreement is going to give you the upper bound. No? So if no one agreed that if the picture is about a rat or, I don't know, a horse, the upper bound will be lower. Okay? So it seems that sometimes algorithms can do better than machines. Not sure about that. Okay, so that's kind of the result of the machine learning pipeline. Okay, so we went from the data to having the labels, having the features, building the predictor, evaluating the predictor. Okay, and I'm going to talk now about the last part of the talk, that is about some practical advice to debugging these algorithms. So you will face different problems when using machine learning. For example, you will get implementation issues related to the data. What kind of analysis can you do to understand what's going on? And some plug and play of resources that are out there. Okay? So implementation issues. So numerical calculations on computers are always subject to errors, okay? And machine learning algorithms are full of mathematical calculations. So something can go wrong in that space. So why numerical errors why we have numerical errors? Because sometimes we have a limited precision in arithmetic, so our calculations are not well defined. Also because sometimes algorithms have limitations, okay? And sometimes, of course, we do careless implementation with bugs or libraries that have bugs and so on. So we have to be aware that sometimes of these problems. And of course, we also always have to do some sanity checks for the deployment, and this is what we call make sure that you have enough resources like memory, computation, and that you have some software engineering sanity checks like unit tests, APIs, and some support. Okay, so also we said that many cases we have problem with the data, okay? Our data is always going to be biased because every data set we said is biased, okay? So sometimes the sampling is weird, sometimes there are misleading categories, the annotation of the labels is wrong or is not very precise. Sometimes we make systematic measurement errors and so on. So all these things, we have to take them into account, especially when we are building a model and then using that model to predict with new examples. Something can get wrong. And of course, we have the problem of balanced data. I'll show you this now. So let's remember that I said that it was very important to sample your data, to partition your data into training set and development set and testing set. And when you do this sampling, when you do this partitioning, you have to be very careful. In this example, we see, for example, different colors represent different labels. So if in your data sets you don't have any examples of the red, you will get 0 in the performance testing. So you have to do this sampling, not only having examples of everything in every partition, but also having a good number of those examples. So this is another example of a little bit more smart way of sampling the data. It is called stratified sampling, and what you do here is to make sure that you have a little bit of everything in each partition. Okay, so as we said, we have to sometimes to do a little bit of analysis to understand what is going wrong with the performance, because the performance of our algorithm is not doing what we expect. So what can be the problem? No, that's a good question. So we have to measure everything. We have to make a good choice of our matrix, because sometimes if that can tell a lot about your data. So maybe your problem is precision oriented and not recall oriented, and so on. So you have to think about those questions, and you have to ask questions to your matrix, and you have to visualize your data in order to understand what's going on. And there are two very different common problems in machine learning, and we see an example of the corpse later on. These problems are called underfitting and overfitting, okay? So when we are doing underfitting, our model is too simple to explain the data, and we are doing overfitting. The model is too complicated to learn from new data. It's too close to the training set. It doesn't have any generalization power, okay? Or there are maybe too many parameters, and this is just making the model too close to the training, okay? So let's see an example of this. And it's a little bit blurry, sorry for that. So let's see that we have some examples, and in this case we have a linear separator that is separating the examples into spaces, and we want the distance from the dots to the line to be small. But in this case, it's an example of underfitting, okay? Because the model is not complex enough to fit the data. This is a nicer way of splitting the data into classes, and this is very clearly an overfitting. Your model is too close to the examples, okay? So if you have new example, it's not going to be able to do anything. It's just, like that. So another way of understanding or interpreting the results is to look at these curves. So you can always plot something like this. So what we have here in the green line is what you want to minimize. So this is, you want to get as closer as possible to this line, okay? So this is your gold standard. And you want your training to be closer when you test the performance to the minimal error. And you want your test also to be closer to this minimal error. But if these two lines are too separate from each other, it means that there is a high variance between what your model is doing during training and what your model is doing during testing. This is high variance, but it's still acceptable. You want your lines to be a little bit closer to the green one. But what you definitely don't want to do is something like this, okay? You don't want your test data and your training data to have very similar performance numbers, because that means that you are clearly overfitting your data. Okay, and after you try to visualize your data, try to understand what is going wrong with your algorithm, it's time sometimes to talk to someone that can give you some advice, okay? And in computer science, we all know that it's hard, sometimes problems are hard to explain and also are hard to communicate, no? Okay, so when we said that we want to plug and play with machine learning, is that my advice is that you try to use as much as possible tested and third-party implementation, and of course to use open source software, and to take care of usability and reproducibility of your implementations, okay? So right now we said that there is too much focus in implementing or developing new algorithms in machine learning, but also some of these algorithms, they are not well documented or understand behind the theory. So you have to go for the things that are, more robust. Established or stable in the community. You also have to have a literary programming, so you have to be a good programmer, and you should use also scientific computer workflows that are going to help you to do this development. There are plenty of machine learning libraries that you can use, for example, in Python. Most of them are open source. Google also released the machine learning library called TensorFlow. There is some, we usually use this kind of libraries to do GPU computing because we want to do fast, complex processing, okay? And also there are some user interfaces that you can use for machine learning. So if you are not very good in coding, you can just use a tool, open your data, try different classifiers, run evaluation, run experiments, all very intuitive. Not very scalable, but intuitive to understand how machine learning works. This is just for later, so you can have all these links or where you can find more stuff about machine learning, courses, videos, and plenty of stuff to have fun with. So yeah, just to wrap up with the talk, the takeaway message for today is that machine learning is about prediction. You want to use your data to construct this predictor, and you want to use expert knowledge in the design, okay? So if you are doing something about, I don't know, air pollution, you might need an expert in that area. Feature engineering is crucial, so you have to work with the features, you have to learn how to characterize the data you have. There is a new trend in machine learning called deep learning. In this case, what we try to do is to learn the features in an unsupervised way. So in this case, we try not to have to get rid of the labels. Labeling data is very expensive and it's time consuming, and you usually need experts. So that's the trend is to do some unsupervised learning of the features, but that's still a very early stages. And a very good advice is split your data carefully, never train in the test set, because that's basically cheating and you think that your model is great, but it's not. And yeah, plug and play and have fun with the machine learning. And I have 2 minutes more, 3. I'll show you a demo now about something we saw before. So this is the demo I showed you before, the slide I showed you before about this reduction project, and what we try to do here is for freedom of information. So we get a text and we have the task to anonymize this text, and usually what we want to anonymize is personal information. So this is just an example. I'm going to open something I copied from the BBC this morning. So there is a text that looks like this, and in this text you can see there are a few entities here, and sometimes I want to redact these entities. It's very fast. So here I have the annotation of these entities by the algorithm, and I can say that, yeah, I agree that I want to redact this person name and so on. And if I export this PDF, I'll do it. I don't know how it's going to look like in this computer. But what we have to do, is it this one? Let me see again. Is to black out those entities that were highlighted, because in the end what we have to have as a result of this demo is that the entities are not visible anymore. I'm not going to download and open the blackout document. It's just that these entities will be blacked out. and sometimes you can make a reason of why you want to black out some of the entities. And this is a very different demo about something very different, okay? So in this case, we use machine learning to navigate and explore a collection of text. In this case, the texts are diaries and letters from soldiers that went to a war. So what we have here is different soldiers' names, and these are all the letters that this soldier, or pages of his diaries that he wrote during the war. And we have classified automatically each of these texts into these categories, okay? And the good thing about this is that these categories has also been induced by the data. It's not that we make them up. So we can see forward. So we can go and see one of the letters that is being transcribed from the New South Wales library. So in this case, it's more like an exploratory tool based on machine learning. Okay? And this is the end of the talk.